So yay for volleyball, yay for awesomeness, yay for going to state. That puts a damper on some of our plans, perhaps. So I'm asking because I don't know where you all are in terms of your plans for the, is this us? Yeah, that is us. Okay. In terms of our plans for the 12th, because I understand that there's like, I don't know, a volleyball game or something. Are there others of you that are planning to not be here on that Tuesday? And it's okay, just let me, I want to know, like if you're thinking that you might be going, okay. So my question for you is, like, I don't want to give a test to an empty room. And I'm excited. I don't want to but we also need to take this test. So my question is, can we like flip these days? Are we okay with taking it like on that Thursday? I know that that's then getting into other testing days. Do you know what I'm saying? Do you guys understand what I'm saying? Or to be that Wednesday is what I was thinking. So Wednesday, the 13th is supposed to be a math and world languages testing day. Is that okay? Or do you guys all have like a calc test that day? Are we okay? Pre-calc, calc people, everybody happy? Okay. So we're going to plan. So I'm going to write this down so I don't forget. And you should write it down somewhere so you don't forget as well. And I'll change it up on Canvas as well at some point. But we're going to flip these 2 days here. So we will do our Unit 4 assessment, except it's a Unit 3 because I'm awesome. Unit 3 assessment on Wednesday the 13th. Does that work for everybody? And then we'll just plan to not do it on that Tuesday so that people that need to be gone or want to be gone can just do that and not stress about having to make up a test. Everybody happy with that? Sweet. If you would like to make corrections on the Unit 2 test, that was the Newton's Laws test, please get those done this week just so we don't have to worry about them next week. Does that sound fair? If for some reason that doesn't work for you, let me know. Many of you made some good progress on it on Friday. Maybe you're done. But if you would like to make corrections, let me know so we can get that done this week. Okay? Everybody happy with that? Okay. I have not looked at the AP questions that I gave you on Friday. I've tried to print them and I can't figure it out, so I need to do it question by question, so I will get there. But if you have not done that, again, please do that just so that when I get to them tonight or tomorrow, we can get there. And then the one other thing that I swear that somebody's playing a really lame practical joke on me. I feel like little silly things are happening, like the fact that this says all work from chapter 8, but really it should be chapter 9. But I don't know why that happened. So if you tried to do your homework yet last night and you were doing things from chapter 8, you're like, this has nothing to do with what we did before, then I'm really sorry. Somebody sent me an email late last night and I fixed it. Yes, that should be chapter 9. So if you did that and you want to negotiate with me about the things that you actually did, then, or if you've just erased them anymore, just like I'm erasing everything. Let me know. But I had intended for you to do this all from chapter 9, because chapter 9 is the Impulse-Pmomentum chapter. So I'm very sorry if that was something that you're like, this doesn't make sense, but I'll try. Good for you for giving it a shot, but it really doesn't, it doesn't match up with what we're doing. So let me know if you need something. Okay. Can we do some physics? Yeah? Yay for physics. Get out some paper. Get out some paper so you can get started. Here's the problem to start. Here it is. A 10-kilogram box initially at rest moves along a frictionless horizontal surface. A horizontal force to the right is applied to the box. Have you seen this problem before? Maybe. It says rank the change in momentum of the box by the force during the 2-second interval indicated below. I'll give you just a moment. Perfect. That's awesome. Okay. I'll give you a couple minutes to look at this. I want to make sure that you understand it. That you understand it inside and not just at a surface level. So go ahead and give that a shot. Oh, all right. Who's objecting? I'm confused about what you're saying, so I'm just going to go. All right. So does this look familiar? Yeah. Yes, because you saw it yesterday. But yesterday I didn't say this because I hadn't written in purple yet. What did it say yesterday? It said rank the impulses, right? And so yesterday when it said rank the impulse, you said, okay, well, impulse, remember that was J, is equal to what times what? Force times time. And the delta, delta, whatever, right? So you got the change in force, the change in time. Either way, how did you rank the impulses? How do you do this? Area under the curve, right? So in order to rank the impulse, you're going to find the area under the curve. Okay. So then today you walk in almost 24 hours later and I throw this brand new problem up. How do you do it? Is it very different? Why not? I seem afraid to say it, but it's really like, it's not very different. Why not? Impulse is the same as delta P, right? Ft is equal to delta P, right? This is change in momentum. This is impulse. So what's the right answer then? I just want to make sure we understand this. Part of the reason I put this up here is to make sure that, because the bell rang and then y'all ran away, and so I don't want to make sure you understood it. So what's the right answer? What's the ranking? Where do we start? B is the biggest? Because we're looking at the area under the curve. Okay, and then which one next? C, and then A, D, and E finally last, and they're all greater than. Everybody happy? Fantastic. Okay, so this seems like I think the reason that you were all so quiet is because it was like, well, duh, Ms. Carmeling, this is kind of a dumb question. But I will tell you that sometimes they'll ask you on a physics test, they won't ask you the impulse part. They'll just ask you to rank the change in momentum from a force time graph. I want to make sure that you see that and that you understand it and you know that those two things, impulse and change in momentum, are 100% interchangeable, right? Because they are equal to one another. It's not a hard concept, but it is an important one. Okay, so we want to make sure that we really get that. All right. Okay, so yesterday at the end of the day, it was really interesting because I had people coming up saying, okay, so what is this impulse thing? It's a brand new thing that you just threw at my head and you haven't really told me what it is. So I want to talk a little bit more about what impulse really is in a very physical way. So yesterday we talked about impulse being like this thing that marketing people use, right? Yeah, so that's why I have 500 tubes of chapstick sitting around my house, but I don't need them all, but my whatever, like that impulse purchase thing. But literally, what is impulse when it comes to physics? So one of the best examples of why we care about impulse has to do with an engineering decision that was made before I was born, when I was a very, very young child, that kind of time frame, that has absolutely transformed people's lives, okay? And that has to do with cars and car safety, okay? My grandfather, who, remember I was gone a while ago to go celebrate his 95th birthday, when I was a kid and we would get in the car, I would have to remind him every single time. You started pulling, I say, Grandpa, put on your seatbelt. Okay? Now, you all have had seatbelts since you were born, right? I had seatbelts since I was born, and it's just like, it's not, you don't even think about it. Like, you put your seatbelt on first, and don't tell me you don't, because if you don't, you need to start. Let me tell you why. Why are seatbelts so important? They keep you in your seat. So let's imagine we're driving down the road, right? We're driving down the road, so you have mass and you're in a car and you're moving. Do you have momentum?
Yeah.
Yes. And let's say that for some reason, and I hope this never happens to you, but let's just imagine that for some reason you're driving along and all of a sudden you have to stop. You have to go from however fast it is you're going to zero. So you go from some big amount of momentum because you're in a car and that has a lot of mass. So even if you're not going very fast, it's a lot of momentum to, if you stop, it doesn't matter how much mass, how much momentum do you have? Right, you have zero momentum because it's m times v. V is zero, momentum is zero, you're done. Okay? So you go from a lot to nothing. You can do this a number of different ways. Okay? 40 years ago, 50 years ago, the teenagers, when they were driving around, totally not paying attention. Stop. What happens to them? Yes, they do. They are sitting in their seats having a great time, and they're an object, and they're going to continue, right? They're going to keep moving until there's an outside force, right? F net equals mass times acceleration. If you find a force that's going to cause an acceleration, what is it that you hit? It could be the pavement. Whee! Right? So you have some projectile motion, and then bam, you're done. Right? You with me here? Okay? Or maybe you're lucky and you didn't actually go through the windshield, but maybe you just hit the dashboard. Is the dashboard very forgiving? Not really. Okay? So imagine how much time it would take for you to hit that dashboard and stop. Is it going to be fast or slow? It's going to be fast. And so if you've got some momentum, right? You've got some momentum, m times v, and you change from that to nothing. So you got m times, I'm going to write it like this, v final minus v initial, where v final is 0, because you're stopped. We know because of the impulse-momentum theorem that that's equal to force times time. The orange side, the left-hand side of this equation is given. You know how big the car is, you know how big you are. You know the final velocity, you know your initial velocity, whatever it was. And again, no judgment, drive safely, but no judgment, right? You're moving at some speed, okay? And then you're gonna go from that to nothing. And you can do that in a few different ways. You could do that either by hitting the dashboard, a very small amount of time, which means a very, very what? Huge force. Okay? 40 years ago, no seatbelts. Big force, lots of death. Are you with me here? And I'm not trying to be like super dark about this, but I'm just being honest. Like that's what we're talking about when we talk about impulse. So then they invent seatbelts, and seatbelts are great because seatbelts, even though they're really tight, like my kids get really mad, right? Like it's too tight, right? Because then you can slow down in a much bigger amount of time, right? Another great thing about these cars is that they have this thing called a crumple zone now. The car that my dad grew up with when he first started driving and whatever, it was just a big box. Are you with me? And they didn't think about this, and so if it hit something, then there is no time between when we're moving fast and when we're not. And so again, the force is going to be really, really big because the time is really, really little. Now they crumple up, and that means that anybody that's in a car seat or with a seatbelt, you slow down much slower. And if the time gets bigger, what happens to the force? It's a smaller force. The less force that your body has to endure, the more likely it is that you will survive. Are you with me here? Okay. So then when I was a little tiny kid, all we had was seatbelts. And then between then and when you guys were born, they added another safety feature that helped make the impulse-momentum theorem even better in terms of saving lives. What was that they added to cars? Airbags, right? Has anybody ever experienced an airbag deploying in their car? I've never experienced it. What is it like, Chris? I'm not, no judgment. I don't even want to know what the story was, but that's okay. Again, no judgment. Like, life happens to people. What happened? Like, did you experience like getting stopped by it? Yeah. So tell me about it.
Big bag, hit you in the face real hard.
So what does it do to your body? Let's think about the physics of it though. So you're moving at some non-zero speed. You go from that to zero, a change in momentum, yeah? Okay, so without the airbag, even if I'm assuming you were wearing your seatbelt, I'm gonna assume that means that there was some increase in the amount of time. But let's say that seatbelt doesn't work or that seatbelt doesn't work super well. The time is going to be increased as you squish into that big bag of air. Like literally that's what it is, my understanding. Again, I've never experienced it, but that's what I've seen in pictures, right? Big bag of air that's going to slow down the amount of time it takes for you to stop, or it's going to increase the amount of time, I should say, for you to stop. And as you increase that time, what happens to the force? It goes down. Okay? I thought I meant to look it up and I didn't. But lives have been saved because of the impulse-momentum theorem. Are you with me here? Like, this is a big, big deal. This is like the most maybe practical of all of the physics that we've talked about in this way, right? Lives are saved by the impulse-momentum theorem and people using it, utilizing it, and understanding it, okay? That was a lot of me talking and a lot of us thinking. I'm going to give you 2 minutes to write that stuff down because we didn't really write anything down. So I'm going to give you just 2 minutes of quiet, write down what we just talked about so that you remember it, so that tonight, 2 days from now, you're thinking about it, you're like, oh yeah, that's what it is. Go ahead and take a couple of minutes to write. That, okay. All right. So hopefully that gives you a little bit of a picture of what, like, why we care, how it matters, right? So it's all about, again, depending on what you want, minimizing and maximizing these two things in order to get what you want out of it. In terms of safety and cars, we're trying to maximize time to minimize force, okay? There are some times when you want to maximize force and minimize time as well. It depends on which kind of thing you're trying to do, okay? I'm going to give you another example. This one is not quite as intense in terms of the amount of people that it affects, but it is something that you may have experienced as well. And Caden, this will give you, we're going to actually do the calculation with this one in just a sec, okay? So another example, this is, I'm thinking more for like people who do athletics, who do gymnastics, who are, I don't know, just like to stand on tables. Because, I mean, why wouldn't you like to stand on tables? Whereas, like, Lauren apparently likes to stand on tables. So here's my question. If I get up on the table, okay, and then I decide I want to jump down. So it's really the jumping down that I'm worried about. And I'm not going to do it because my shoes are not appropriate for jumping off of tables today. But let's say that I do jump off of a table. There are a couple different ways that I can go about jumping off of this table. Okay? I jump off the table, and it's really all about the landing. Good idea, bad idea to lock out my knees? Bad idea. Why is it a bad idea? Tell me the physics of why it's a bad idea. Emma, you look like you want to start. Can you tell me some words?
Your legs are just straight. It's the whole landing process takes less time than it would if you were landing. So the force is bigger when you're moving.
Yeah, it hurts. Like you can break your knees, right? Like this is bad, and we're going to do the math to figure it out for sure. But let's just make sure we understand this. So when we're talking about a person, so they're standing up on a table or whatever, they're starting off at a velocity right when they get close to the ground, right? And then the ground is going to push up on them. You with me there? So they start off with a velocity, and we can calculate that velocity because it's just kinematics. It's just something falling. So there I go, whee, and then I'm going to fall. I'm close to the ground. You can figure out what that's going to be, right? That speed, okay? That's my initial speed. My final speed is 0 because I'm stopping. And I know my mass, okay? So the time, if I lock my knees, there is no time. Like it's so fast between when I hit and when I stop. Very small, it means the force would be very, very large. Whereas if I bend my knees, then it's just like the airbag, right? It gives my body, and we call it our center of mass. That's like what's actually stopping is my center of mass, which happens to be right around here. It gives it more time to stop. And by giving it more time, it means the force is much, much less. Okay, we're going to do the math today. So here it is. So here's the situation. I need to retype it someday, but, who has time for that? All right. So this came from some book. It was example 7.5. Calculate the impulse. We know what impulse means? The impulse experienced when a 70-kilogram person lands on firm ground after jumping from a height of 3 meters. Okay. Then it says to estimate the average force exerted by the person's feet on the ground, blah, blah, blah. So we'll get to this, but let's do part A together, shall we? then I'm going to let you do part B kind of in pairs, and we'll work it out. So we've got a 70-kilogram person jumping from a height of 3 meters. Now, friends, 3 meters is kind of high. I just want to make sure that we're understanding this. That's 3 of these stacked up. 1, 2, 3, up there, really high. Okay, so I just want to make sure you're really understanding what we're talking about. We could do it from 2 meters if you would rather. I don't care. But this one's written as 3. I just want you to understand, like, that would be pretty high, but not a good choice. Okay, let's not do that, especially not with our knees locked out. So, I don't know where to start, so I'm going to start writing down my givens. And to be clear, friends, we've kind of gone through this, and I've told you this before. Are you going to have a question that's hard on a test? No, but the concept is really important, and that's what I want you to see. And sometimes numbers just make it easier to conceptualize. So let's do that. What do you know? What's something you know? Help me out. I'm going to write 70 kilograms. Thank you. Me and TI. It's all good. All right, so 70 kilograms is the mass. What else do you know? You know that the height is 3 meters, so I could write that as delta y, right? How far down is that person going to go? 3 meters, so negative 3 meters going down. All right. And then it asks you to calculate the impulse. So impulse is, how do I write impulse? Force times time, or J, or using the impulse-momentum theorem, I could also say that it's the mass times the change in velocity. So all of these are interchangeable, friends. I don't know the force, because again, this is the force of the floor pushing up, right? That's the force we're experiencing. I don't know that, and in fact, I really don't know that, because in part B, it asks you to calculate that, so I really don't know it yet. Can we find the mass times the change in velocity? Yeah? Sure we can. We know the mass already. Yay for us. Do we know the change in velocity? Can we find it? Okay, so the change in velocity is we need the mass, and we need the final velocity, and we need the initial velocity. The final velocity is what? 0. Little kinematics fun for you today. Get out your equation sheets if you need them, and find out the velocity when the person gets to the floor. I'll let you go ahead and do that real quick. I like this problem again because it's not super challenging. It's not something that I would expect you to do on a test, but it's nice to kind of see how big these numbers can. So let's double check, make sure we're all on the same page. So the equation you're going to use is the squared one, right? VF squared equals VI squared plus 2A delta Y. And from that, you can find the final velocity. And what did you guys get? How fast? You just told me you had it, didn't you? Or was I dreaming? 7.67? So that's the final velocity. That's the velocity when the person gets to the floor.
Oh, it's never mind.
Do you want me to go through that quick?
No.
So
This is negative, and that's negative.
yeah.
So when you take the square root, it's a positive. But remember, when you take a square root of something, it's plus or minus the square root of it.
I have 0 equals velocity initial squared plus 58.8.
Okay, hold on a second. So let me just make sure we're good. So here, this is going to be VF squared. So VI squared goes away. So you just have 2A delta Y. So, okay, let me back up. We have too many initials and finals. I apologize. Okay, so in order to find, there we go. In order to find the speed when the person hits the floor, we need to say that the initial velocity at the top before the jump is 0. And the final velocity here is the final velocity at the floor. So that's before the floor applies any force to the person. So the only acceleration that we're experiencing in this part of the story is just the acceleration due to gravity. Okay? So you've got an initial velocity of 0. We're trying to find this velocity at the floor. That will be the initial velocity for this part. The trick is that we've got multiple initial and final velocities, and I apologize for that if that was confusing to you. Does that make more sense now? Okay? So again, initial velocity before the jump, final velocity at the floor. That velocity that I'm getting is VF is equal to, it's going to be plus or minus because it's the square root. We know it's going down, so it's going to be negative 2 times negative 9.8 meters per second squared times negative 3.0 meters. I know it's going down, so I know it's going to be negative 7.67 meters per second. Why is what 2?
Why isn't it 1/2 acceleration times?
That's a different equation, sweetheart. Yep, so I'm looking at the VF squared equals VI squared plus 2A delta Y. I think it's the third equation on your equation sheet. Yeah. Okay, how are we doing here? Are we okay? So that's the speed with which you would hit the floor if you jumped from 3 meters up. Don't jump from 3 meters up. Find the ladder. Okay? But if you decided to, I don't know why you would, but let's say you did. Okay? Now, can you figure out the impulse? How do you find the impulse? The impulse that they would experience. M delta V. So delta V is going to be 7.67 times 70 kilograms. What do we get? Go ahead and do the math, friends.
Why is velocity final now velocity initial?
Okay, so this is the initial before the jump. This is the final when we get to the floor before you hit the floor. Do you understand what I'm saying?
Well, I don't know how you get to the floor without hitting it.
So like when I ask you how fast the frog is going when it hits the floor, it's this fast, right? Once the frog gets hit, once the person gets hit, once the floor and the whatever interact, then it applies a force to stop it. It accelerates it at a much higher rate than the 9.8. Does that make sense? Yeah. And we can do that math in a second. What's what? You guys okay? Okay. So what did you get for the impulse, friends? I feel like when I ask a question like that, y'all like, oh, but I thought you did it already. So you're going to take 7.67, right, or 70 kilograms times 0 meters per second minus negative 7.67 meters per second. Are we okay? And you multiply that, and you're willing to tell me an answer, maybe. That is your impulse. What did you get? 536.9 or something like that. What are the units? Can be Newton seconds, or it can be kilogram meters per second. Is there a difference between the two? One takes more graphite to write? Yes. But other than that, they are exactly the same. They're equivalent, we'll say. Yes, either one is fine. Okay. So this is a little bit complicated, but we can do this. So regardless of how you land, regardless of whether you lock your knees out when you land, whether you bend your knees, whether you hit a trampoline, I don't care what happens. The impulse that you experience is this. Do you agree? Okay? The impulse will be the same regardless because you have the same change in momentum. Same mass, same change in velocity, same change in momentum, same impulse. So now we want to figure out which is a better choice. I think we probably know, but we want to see how much different it is. Okay? So here's the situation. The stiff-legged person, their body will move about 1 centimeter between when they hit and when they stop. This much, okay? The second case, the bent leg person will move about 50 centimeters. Go down like that, right? You're going down like almost half a meter to absorb that shock. Okay? We're going to split you in half so that we can do some, make it this a little bit efficient. So we're going to go 1, 2, 3. You guys over here are going to do, why don't you guys do the stiff leg? And 1, 2, 3, you guys are going to do the bend leg. Okay? You have to talk about this a little bit to figure it out because it doesn't give you a time, does it? So you have to find how long it's going to take and then use that to figure out the force. Okay? I'm going to let you work for a minute because I know that you have the physics to do this. It's not going to be instantaneous though. You got to figure it out. All right, my friends, I just want to make sure that this is making sense to you. This problem is kind of big and messy, but I think it's really like, if you can get your head around what's going on here, there's a lot of really interesting physics, okay? So here's the first thing that I want to make sure everybody gets, is that regardless of how you fall, or how you land, I should say, every person that would jump from 3 meters high down to the floor would experience this change in momentum. You okay with that? Because right at the floor, as soon as your feet touch the floor, you're moving at 7.67 meters per second. And you've got this much mass. And you're stopping because the floor is going to stop you. So you've got a mass and you've got a change in velocity. So no matter how you stop, you will experience this much of a change in momentum. And any change in momentum means there's a change in velocity, means that there's a force that's acting over some time. So the thing that you have to figure out is how much time it takes. So I want to just take a peek here real quick, just kind of looking at the time here. I'm going to look at the locked knee version. Yeah.
So does that mean that there's a relationship between the acceleration and the impulse?
Absolutely. In that the acceleration is equal to, acceleration is force divided by mass, right? It's all intertwined. Yes. This is just a different way to sell the same product, right? Same stuff, just in a different form, because I think this makes more sense to you, to like the idea of it, right? Okay, so the locked knee person has a change in height from when their feet touch the ground to when they stop of 1 centimeter, which is 0.01 meters. You with me there? Not very much. It's got a change in velocity, or we'll do final velocity initial. So the velocity when they hit the floor is 7.67 meters per second, and the velocity when they stop, is 0. And we can use that to find time. Okay, again saying 1/2 VF plus VI is equal to delta Y over T. I'm going to just go through this real quick and say that I got a time, correct me if I'm wrong, of 0.0026 seconds. Is that what you guys got? Okay, if it's not, I can go through it with you in a second. I want to make sure that we're kind of getting there. It's very, very short. It's not very long, that time. If you know that, and you know that the force times the time equals 536.9 Newton seconds, then the force equals 536.9 divided by 0.0026, which gives you a force. The force that I got when I did it was 2.06 times 10 to the 5th newtons. Does that sound like a lot of force? 10 to the 5th? 10 to the 5th? That's 206,000. 1, 2, 3. This is the poor choice. Yeah. So this would break your kneecaps, is what I'm saying.
Yeah.
Yeah. So it is a lot of force. Yes.
Oh,
Yes.
that's what I meant.
That's what I'm saying. Yes.